Welcome to the chest X-ray disease diagnosis. We are team 09. Next, please. This is the agenda. Next, please. So why this project? We chose this project because X-rays are the oldest and most frequently used form of imaging, and they require significant experience skills to really read it accurately. And in underdeveloped and developing countries, it's difficult to find trained clinicians who can do this accurately. And so this makes it analysis of X-rays costly, time-consuming, and prone to error. Next, please. But this is a literature survey. We read about the convolution neural networks, deep learning, Chexpert. We read about the efficient nets, GradCam, and sparsely aggravated convolutional neural networks. Next, please. So this is a system specification. We used PySpark on the hosted Domino Data Lab for exploratory data analysis. For machine learning, we used Python with TensorFlow and Keras APIs on local machines with GPU and Azure virtual machines with GPU. We utilized the low resolution 11 gig data set. Next, please. As you can see on the slide, the volumes of data set is shown, and the volume of parental and little views is shown. As also shown, the training labels are highly unbalanced, and majority of the labels are from negative class. Next, please. So we performed the same pre-processing as Chexpert paper. We followed the same approaches, U0s, U1s, multi-class, and you ignore. We also did normalization, which helped in convergence, better convergence, faster convergence, I would say.
So we started our approach to just train DenseNet 121 or the 14 pathology without doing any data imbalance handling. First, just create a baseline. The next, we applied weighted loss function and focus on only the 5 pathology Chexpert focused on. So we applied transfer learning with weighted loss on DenseNet 121. The next, we try DenseNet 121 instead of using pre-trained ImageNet weights, we use ChestNet weights because the ChestNet is ChestNet DenseNet model is already trained on chest X-ray images. We think pre-trained weights from ChestNet is probably going to give us better result. The next, we try the EfficientNet with ImageNet pre-trained weights. EfficientNet is supposed to be a more accurate and less lightweight model. Then next, we apply image augmentation techniques. So random rotate images from -45° to 45°, because we're seeing some training data tilted to left or right. Also, we'll apply random contrast, random saturation, and brightness to the images. So here are the detailed 5 experiments we have done. Please scan through them. Then this is our project result. Our best model overall on average is by using U1's labeling strategy. And you can see by using weighted loss, apply weighted loss function. So if you can see this model without weighted loss, the EUC is pretty horrible model, not able to distinguish positive and negative class. You can see here after apply weighted loss, we improved model accuracy significantly. And you can see image augmentation improved model accuracy for EfficientNet B3. And here, the PR-EUC curve, you can see the model is have very even trade-off between false positive and false negatives. So the result for the other labeling strategy are in following slides. You can spend some time to look through them. But here I'm gonna just go skip to the visualization part.
All right, so for visualization, we use the GradCam to accurately pinpoint the pixels which contributed the most towards the classification of pathology. So we have described our process, and here is one of the example of the GradCam. Can you please go to the next slide? So in terms of conclusion, at the end of the day, no one labeling strategy stood out as a winner, but on an average, we think U1 was better than the remaining three labeling strategy. And also, lastly, we think that even though our model accuracy was lowered compared to the Chexpert paper, however, we still think that our initial hypothesis that convolutional neural networks are well suited, or convolutional neural network architectures are well suited for image classification, that still holds true, and we certainly believe it's one of the best to train models using CNN architecture for image classification problem. Can you go to the next slide, please? So this is the future enhancements. Primarily for future enhancement, we think that if we had more time, or in the future, if we redo this project, we would try to use the higher resolution image dataset, which contains images which are of higher image quality. Secondly, we would try to handle the imbalance problem by using some methodologies like SMART, and also do some feature engineering. One of the another important thing that we think we should be doing, or we will do in the future, is we used transfer learning without just training the actual convolutional basis, but we intend in the future to continue training the transfer learning model by unfreezing more later convolutional layers with the hope that it helps to improve the model. And lastly, work on fine-tuning the hyperparameters like learning rate, activation function, try different epochs, etc. So those are some of the future enhancements that we think we will be doing in the near future, or we would have done if we had more time. And this concludes our presentation. Thank you so much for your time, and we look forward to hearing from you for our project. Thank you so much.